Hey class, in this recording we're going to focus on how we physically take a sound wave and turn it into an action potential. So as we're looking at, give me a moment here, I want to get the colors up. My colors, my pretty colors. Um, as we're looking at the inside of the inner ear, we have the cochlea, and inside the cochlea, that this is a tongue twister for me, the seashell shaped organ, we have cochlear hair cells. And so when we vibrate the malleus, incus, and stapes, that is going to cause the oval window to vibrate. As the oval window vibrates, that's going to transmit the vibration to the fluid inside of the ear. And as that basilar membrane is going to be vibrated by the fluid underneath the ear, it can vibrate very quickly. It has up to 20,000 times per second. This maximum vibrational frequency is the upper limit in terms of the highest pitch noise that we can hear. Human beings typically can't hear a noise above 20,000 hertz. And as the basilar membrane within the inner ear, within the cochlea, is vibrating, it's going to cause some hair cells to move. Some of those hair cells are referred to as the stereocilia if they are the outer hair cells. And they have a very high potassium fluid that bathes them. This fluid that has lots of potassium ions is referred to as the endolymph. And we can see endolymph right here, directly around those hair cells. And those endolymphs create a very unique electrochemical and the endolymph creates an electrochemical gradient with the potassium ions, so that the outside of the cell is positive 80 millivolts and the inside of the cell is negative 40 millivolts. And as we look at this hair cell, the very tip of the hair cell is going to be embedded within the tectoral membrane that is receiving those oscillations, those vibrations from the auditory ossicles. So as we look at the stereocilium, those hair cells that are all lined up, we find that there's a single protein at the very tip of those hair cells. And if we zoom in on that single protein is going to attach to the hair, or have the hair attached to it. And that stretchy protein tip, sometimes referred to as a tip link, connects the end of one stereocilium to the next stereocilium. So in this figure, we have protein tip links. We have protein tip links connecting our stereocilii together. And as we look at these stereocilii, our tallest stereocilium is going to be bent when our basal membrane raises towards the tectoral membrane. So movement of these membranes is going to cause the bending of these hairs and the tip links. So then we bend the hairs, and by pushing the hairs over, we're going to apply pressure to the tip links. That will cause the tip link to mechanically be pulled or stretched out of the way. This will make room for potassium ions to flow in. And as we have potassium rushing in, we're going to have a depolarization of the membrane, which then causes an action potential and a release of neurotransmitter. This signal, this action potential, is then, this depolarization is then going to stimulate additional sensory dendrites through the release of the neurotransmitters to generate another action potential on the cochlear nerve. That cochlear nerve will then merge with the vestibular nerve to form the vestibulocochlear nerve, and that action potential will be sent to the brain to be processed as sound. So, as we're looking at sound, loudness or amplitude, so what's the difference between two identical noises that are quiet and loud? The difference is the amplitude of the sound wave. So as we look at soft sounds, they produce relatively short up and down motions. So here's my sound wave. Try to pretend that this sine wave is all even. And if we look at a loud noise, this loud noise will have the same frequency, but amplitude of the sound wave would be much higher, causing the pectoral membrane and basilar membrane to oscillate farther, but it's oscillating farther, but it's also oscillating at the same frequencies. So that loud noise makes the membranes oscillate more vigorously. That triggers a higher frequency of action potentials. So this is something that's kind of unique. The frequency of action potential is used to determine the loudness of the noise. High frequency action potentials are interpreted as a louder sound. It is not interpreted as a higher frequency noise. So as we look at the pitch, so we talked loudness, let's talk pitch. As we look at the pitch, so high pitch versus low pitch, that depends on which part of the basilar membrane is vibrating. If we're vibrating the proximal end of the basilar membrane, that's very close to the auditory ossicles, that's going to be considered a high-pitched noise. Our brain interprets the proximal end vibrating as high-pitched noise. And then if we look at the distal end of the basilar membrane, this distal end of the basilar membrane is wider and more flexible. And when that's oscillating or vibrating, that's interpreted as a low-pitched noise. So if we were to look at how these signals get into the cochlear duct, or the low-frequency noises don't cause the first region of the cochlear basilar membrane to oscillate, but they do cause the distal region. And conversely, let's go back to blue here. High-frequency noises cause the proximal end to vibrate and effectively do not influence the distal end. And then we have the medium frequency noises that are the in-between ones. Sometimes people lose the ability to hear. This is referred to as deafness. There are two kinds of deafness. We have conductive deafness and sensorineural deafness. Conductive deafness is a kind of deafness that is going to involve a loss of conduction, a loss of transmission of the vibrations to the middle ear. So damage to the eardrum, damage to the middle ear, the bones of the middle ear. As we look at the auditory canal, maybe there's a lot of earwax or cerumen that has blocked it up. Or maybe the bones of the little ear have become very stiff. We have otosclerosis. That this condition, otosclerosis, will form or happen as the auditory ossicles, the malleus, incus, and stapes, fuse together. And as these auditory ossicles fuse together, they lose free vibration. And if they lose the ability to freely vibrate, then the tympanic membrane doesn't receive the signal that it's supposed to receive. And all noises, generally speaking, are going to be quieter. We also could have sensorineuronal deafness or nerve-based deafness. And this is deafness that occurs when the hair cells inside of the inner ear start to kick the bucket. So as we have damage to the hairs in the inner ear. So another way to think of this is deafness due to exposure to loud noises. So people that work in factories are oftentimes exposed to loud noises. Drummers, especially, or musicians, or construction workers. So students wear hearing protection, even for mundane things like mowing the lawn. I know several recordings ago I mentioned how my dad lost 1/3 of his hearing when he was a kid. And because of that, he has been paranoid about wearing hearing protection his entire life. And now that he's in his 60s, his hearing is now normal for his age. He has age-adjusted normal hearing because he's done such a good job protecting the hearing that he had left that he now has been reestablished as normal hearing, which is to say that he's getting to be an old man and he's hard of hearing and I have to yell when I want him to hear me. Oop, I clicked the wrong button there. There we go. So, class, if you have any questions, please feel free to post them on the class discussion board, shoot me an email, or talk to your friends. And as always, happy studies.